In this video, we will discuss greatest common divisors. Before we define the greatest common divisor, we first need to discuss what it means for one integer to divide another. Suppose for two integers a and b, there is an integer q such that a is equal to b times q. Then we say that b divides a. Alternatively, we could say a is divisible by b, a is a multiple of b is a divisor of a, or b is a factor of a. All of these statements are equivalent. This notation should seem quite familiar. In a previous video, when we introduced quotients and remainders, we expressed the division of a by b by the equation a equals b times q plus r. Using this definition, we say that b divides a if the remainder a mod b is equal to 0. In other words, a is equal to b times q plus 0. Let's do two examples to illustrate the concept of a divisor. For the first example, let a equal 30 and b equal 15. In this case, we see that the remainder 30 mod 15 is equal to 0, so 15 is a divisor of 30. The quotient 30 div 15 is equal to 2, so we can write 30 is equal to 15 times 2. For the second example, let a equal 27 and b equal 4. Using our techniques for finding the remainder, we see that 27 mod 4 is equal to 3. Since this is not a 0 remainder, we know that 4 is not a divisor of 27. Try these two examples on your own. Calculate a mod b first, and if the answer is 0, calculate a div b. For a equals 50 and b equals 25, 50 mod 25 is equal to 0, so 25 is a divisor of 50. The quotient 50 div 25 is equal to 2. For a equals 49 and b equals 2, we see that 49 mod 2 is equal to 1, which is not 0, so 2 is not a divisor of 49. Now we can talk about the greatest common divisor. Let a and b be integers. The greatest common divisor of a and b is the largest natural number g, such that g divides both a and b. We often denote the greatest common divisor of a and b by GCD of a and b. In the special case that the greatest common divisor of a and b is equal to 1, we say that the integers a and b are coprime. Let's illustrate one way to find the GCD when a equals 12 and b equals 10. The naive way to find the GCD is to list all of the divisors of each integer and then find the largest divisor that is in both lists. The divisors of 12 are 1, 2, 3, 4, 6, and 12, while the divisors of 10 are 1, 2, 5, and 10. The largest divisor that appears in both of these lists is 2, so the GCD of 12 and 10 is 2. While the naive method works well for small integers, it becomes very impractical as the integers grow in size. In a future video, we will present an algorithmic way to calculate the GCD. Before we do some examples, we will state two theorems and a few special cases that describe properties related to the GCD. The proofs for these theorems can be found in the text and are stated here without proof. The first theorem states that if a and b are two integers, then the GCD of a and b is equal to the GCD of b and a. In other words, when finding the GCD, the order does not matter. The second theorem states that for a natural number g and integers a, b, and q, then the following statements are true. Statement 1. If g divides both a and b, then g also divides a minus the quantity b times q. Statement 2. If g divides A minus the quantity B times Q, and G divides B, then G also divides A. Statement 3. The GCD of A minus the quantity B times Q and B is equal to the GCD of A and B. Statement 4. The GCD of A mod B and B is equal to the GCD of A and B. There are three special cases to consider. For any non-zero integer A, the following statements are true. The first is that the GCD of A and A is equal to the absolute value of A. The second is that the GCD of 0 and A is equal to the absolute value of A. And the third is that the GCD of 1 and A is equal to 1. To get some practice, try calculating the four following GCDs. Here are the solutions for each of the four example problems.